Everybody for joining. This is basics of seismic design, and the reason I want to talk about that is because I feel like there's this misconception that seismic design has to be complicated and costly to the owner. So I kind of want to demystify that and um, just talk about the structural engineer's perspective and how we go through our design process. So let me share my screen here. Okay, real briefly, CDG engineers, for those of you who aren't familiar with us, we're a full service, multidiscipline engineering firm with services in civil, structural, mechanical, electrical, as well as architecture. And we work in the market segments of infrastructure, power, mining, and heavy industrial. The structural engineering department within CDG, we have 12 full-time engineers, 9 of which are PEs, 3 of which are SEs, and then 3 EITs. Because we're multidiscipline, we really have a wide range of services, and our structural group, we support all of those, and we're lucky in the fact that we get to work on all different kinds of structures. And these are just a few that we do: industrial equipment structures, existing structures, infrastructure, and foundations. I'm the assistant department manager of the structural group. I have over 10 years of experience. And again, I really pride myself and feel lucky that I'm able to do so many different types of structures. And I've really had a wide range of experience in my 10 years. So the presentation today, talk about basics of seismic design, how forces are determined, site considerations and the impacts, building considerations when you're planning out your building, laying it out, things for the owner to consider. Then our seismic force resisting system for buildings and non-building structures. Then briefly talk about foundation design and existing building modifications. So basics of seismic design. How are forces determined? All of you know that earthquakes cause ground motion. Will that lateral displacement translate to lateral forces proportional to the structure's effective weight? In other words, the analogy I'm going to use here is imagine a spring. If you can see my cursor, imagine a mass on top of a spring, and that spring is attached to a table. And then you bump that table. Well, momentarily that mass is going to stay where it was, and the table moves, and it's going to try and get back to equilibrium centered over the spring. Well, springs have a spring constant, a force per unit length. So that's kind of really simple basic of what happens, but it gets more and more complicated because our building has a series of springs, beams and columns, and the ground motion is more complicated than just a simple displacement. Here's a seismograph, and this is the ground acceleration with respect to time. So you have these oscillations, these jolts back and forth. So how do you equate that? How do you turn that into forces? So I'll be talking about the equivalent lateral force method. This is kind of a simplified method. It's code mandated, and this covers most every structure we run across. And then how forces are applied and distributed. So base shear, many of you have probably heard that term. We come up with this seismic response coefficient, and there's a lot of parameters that go into that. This is just the really simple equation to get to it, and then that coefficient is multiplied by the building's total effective weight, and so that's your base shear. And then you distribute the loads both vertically and laterally, depending on the building's stiffness and where those weights are located within the building. Horizontal distribution is taken care of by diaphragms, and diaphragms are, there's flexible and rigid. Rigid diaphragms would be like a concrete floor in a building, and a flexible diaphragm would be a roof, corrugated metal, the deck. So what impacts the magnitude? Large masses at high elevations. Again, go back to that analogy of the mass on top of a spring. What if that mass was 2 times as big as you originally thought in your mind? Well, that's going to cause a lot bigger displacement, more forces. Site location, I'll talk about the importance of a geotechnical investigation and the ramifications of certain locations, and then the soil conditions. And then I'll talk later about the structure's response to ground motion and its ductility and its ability to dissipate energy. So one thing a lot of researchers do is perform a shake table test. They'll mock up a full-scale shear wall or moment frame and program a shake table to mimic that of a seismograph. This one in particular is from the Northridge earthquake in 1994 in California. So I was going to show you a YouTube video of that, but then I thought, why not employ my own lab? So here we go. This is my daughter, my eldest daughter. She's the engineer here. She's just mocking me right now, saying earthquake resistant thingy. This is Audrey. She's the architect of this operation. She's talking about Harry Potter wearing jammies. But all right, so Emma's performing the shake test, ground oscillations, and well, okay. So our design wasn't that great, but I blame the architect. Okay, design criteria. Site impacts, the mapped spectral response acceleration. Many of you have probably seen a map similar to this, and this is the mapped spectral response. And you all know that the region closest to us, New Madrid, is the kind of epicenter of these high forces. But it's still a significant concern in St. Louis. So. Soil site class. So it's really important to get a geotechnical investigation and get it early on during the project. So the geotechnical engineer will tell us what site class it is, and it's A through E depending on how stiff the soil is. If we have no other information and the owner does not want to get a geotechnical report, we have to assume D. D is the default. That translates all the way through the project. If we have to assume D, then that increases our seismic design category. And our seismic design category directly increases the forces that we have to apply, the seismic forces that we have to apply. So building considerations, again, trying to demystify the complication. I hear a lot of people say, well, we don't need a design for seismic. Our building's not that important. Well, it is required by code, and it doesn't have to be that big of a deal. And we're not designing for it to be seismic proof. That would be extraordinary and impossible, very costly. So we're designing for acceptable risk. The goals here are to avoid injury and loss of life, minimize the damage and the repair cost to you, the owner, and maintain functionality in those critical structures. This diagram down here is a good representation of that. And we categorize these into an occupancy category or a risk category. 4 is to maintain operation during a seismic event. So these would be hospitals, police stations, emergency structures, also power. We need to keep power to everybody. 3 would be immediate occupancy. These are high occupancy buildings, schools, anything with a lot of people in it. 2 is life safety, and 1 is collapse prevention. And these are really low occupancy storage buildings or agricultural facilities, things that don't have a high risk to human life. So And then another thing in building considerations when you're planning out your building is to try and avoid irregularities. And I say buildings, but buildings or any other structure, non-building structure. Building irregularities. Here's a few diagrams. I talked about those heavy masses at high elevations. Well, that's a irregularity that we have to design especially for. Another one would be a soft story that, like, say you have a tall atrium on your bottom floor, and then all subsequent floors above that are stiffer and smaller. That's an irregularity. A horizontal irregularity, a common one is reentrant corners. If you have two wings of a building, that intersection point is another design obstacle. Diaphragms, if you have holes in your diaphragm. I mentioned before how diaphragms help distribute your lateral loads to different frames and bays. If you put a hole in it or cut a weird shape out of it, it's gonna result in more design. Also, with irregularities, depending on the type and the severity, we have to increase a redundancy factor, which is 30%. That's an additional 30% to the seismic loads. So again, we can design around these, and it's not that big of a deal, but it will save you, the owner, money in the long run if we can avoid those. Seismic force resisting system. So now we've talked about our building layout. Now we need to select the seismic force resisting system. That's the lateral and vertical resistance to the seismic forces. Building height is important, and materials is important. And this is out of the code. I know you can't read this, but it's dependent on the seismic design category. This is the system, and depending on the system you want to use, it's either permitted or not permitted, depending on the building's height and the seismic design category. So let's take a steel, for example. The two basic systems are moment frames and brace frames. Now, if you get in a higher seismic design category and the building height gets beyond a certain point, 35, 60, and 160 are kind of the benchmarks, then you may have to go to either intermediate moment frames or special moment frames or special brace frames. And it means that the building system can dissipate the energy better, and you get a benefit in the structural design by reducing your loads because of that. However, it costs more because there's more detail and design requirements involved with that. So at concrete, seismic force resisting system, your basic ones are moment frames or bearing shear walls. So the frames and bracing play different roles. I talked about diaphragms, load, and frames and bracing. In a steel structure, generally speaking, brace frames are more economical. Moment frames are a lot of times desired because you want that open space and be able to walk through the bays and for architectural reasons. Buildings versus non-building structures. I keep talking about buildings, but non-building structures follow a similar procedure and similar analysis. There's just a little bit different design criteria. And then for some structures like bridges, transmission towers, and hydraulic structures, there's different codes that govern that. They're different enough from buildings that we need to look at it a little bit differently. Design methodology. So now we have our building layout. We've selected our seismic force resisting system, our materials, concrete, steel, masonry, whatnot. Now we need to design it. So stronger is not necessarily better, at least not for all members. There's a thing called ductility, and that, just to define that, it's the property of elements to continue to carry loads past their elastic limit, yielding. So this is planned for. It helps dissipate energy, and that goes back to what I was talking about, is certain heights and seismic design criteria. You're required to use a better system that helps dissipate that energy more. Also, ductility we use to protect the non-ductile elements. Non-ductile elements are critical items like connections, beam to column connections, and the column to foundation connections. We really need to protect those elements because if they fail, it's a non-ductile failure and it can be catastrophic because everything hinges on that one point. So in order to do that, we decide what should yield for first. We actually plan on what yields. So it's this weakest link mentality. So going back to the steel brace frame example, if you have a brace, we designed the connection to be able to take the maximum yield strength of that brace. So in other words, we're in a seismic event, a really big seismic event. We're actually planning for that brace to potentially yield and fail, but it protects the connection and the more important elements. Again, for life safety, to keep the building standing, keep those vertical elements, keep the integrity of those vertical elements so people can escape safely. That being said, more flexibility, more ductility reduces your seismic loads. However, we need to also look at deflections. There's allowable story drifts, code mandated, and then there's seismic separation to adjacent structures. We don't want our building oscillating too much and bumping into adjacent structures and causing other kinds of damage. Example project that we CDG did recently. This is in a high seismic area near Cape Girardeau, poor soil conditions, and it's tall with a lot of heavy equipment at high elevations. So we had to use a special concentrically braced frame system. And what that meant is it's more more intensive design, but also more detailed requirements for the fabricator. So we found, in this project, especially so, it was good to have an open communication between us, the engineer, and the fabricator to make sure that they're getting the design intent that we put on the drawings. Foundation considerations. I talked about the importance of getting a geotechnical engineer for the site characteristics and how it affects the seismic forces. But once we get down to design the foundation, it's also important. We need to know the soil conditions and what kind of capacity we can get out of it. What is the quality and depth of soil layers? Slope stability on certain sites is an issue, and then liquefiable soils. It's uncommon, but we ran into it on a project a year or two ago. There's layers, and what liquefiable soils are is there's sandy layers that are below the water table. And so in a seismic event, when the ground shakes, that turns into soup. And you can't you can't put your foundation on it for obvious reasons. And it affects deep foundations. So in this case, we had to go deep foundations and design, especially for these liquefiable soils. Geotechnical engineer can also give us recommendations on deep versus shallow, depending on the quality of the soil and settlement. So what is the acceptable, what is the owner willing to accept as far as settlement and differential settlement? An inch of settlement in one part of the building can cause major issues to the structure throughout. So it's something to consider. And then what's required by code. If deep foundations are required, there's specific design and detail requirements. Say a drilled caisson needs to be reinforced to a certain depth in certain seismic design categories. Also, you may need seismic ties or grade beams is another name to connect those together, and that's what's pictured here. These are seismic ties spanning between pile caps. These are actually concrete pile caps with about three. Depending on each one, about 3 H piles each. Existing structures, existing building modifications. There's the question: what constitutes a seismic evaluation? If your building was built, say, in the 1950s, does it really need to meet today's codes if you touch it? The answer is not necessarily. We go to the International Existing Building Code, the IEBC, and they define it in 3 major categories: repairs, alterations, and additions. Repairs are just that, repairing something that's damaged. Alterations is altering something within the existing footprint, and additions is adding to the footprint of the building. So alterations is probably the easiest one to look at here. Is you want to modify something. It depends on how much of the seismic force resisting system you're impacting, or if you're adding loads to it. And again, they have subsections of this. Is the level of alteration and repair and addition may require you to do more evaluation than others. So it's important to hire an engineering firm to sift through the code for you, look at your specific project, and I suggest hiring somebody early on in the planning process to help steer your project. If you can be just under that 15%, then you could end up saving a lot of money. Don't cut that brace. I've been to different industrial facilities and elsewhere, and I've seen people cut braces, and I understand why. They can be in the way and they can be annoying. This was a poor design in the beginning, poor layout, I should say. You can see that this brace that used to go down to here is right in the walkway. They had to climb over it, and it was extremely annoying. So I don't blame them, but they cut it off. If you run into this situation, again, hire an engineer. We could come up with another solution that doesn't have a detriment to your lateral force resisting system. It keeps the building integrity or structure integrity. In this case, maybe we could have looked at converting this to a moment frame system or relocating that brace to somewhere that's more convenient. So in summary, I covered a lot here, hopefully not too quick, and hopefully it didn't overwhelm you. So the things I'd like you to take away from this is, for an owner trying to save money here, is get a geotechnical investigation. Hire an engineering company early in the planning process. A lot of times we'll do a preliminary design phase for clients, and we'll help them walk through the building or structure planning. We can look at those things about masses at high elevations, building irregularities, and kind of guide you into a more economical solution. A lot of times it can't be avoided. For example, this bunker structure, this is in New Madrid. There's one large or 2 large conveyors that aren't on it yet, but that's a high mass, high load at a high elevation. So you can see this particular structure is pretty beefy, but it's a high seismic area. And in fact, this is the structure that had the liquefiable soil. So these are founded on drilled caissons. Determine the design criteria, and that comes with hiring an engineering firm. We can walk you through the process and determine your seismic design category, those occupancy category and risk category. Don't plan on heavy equipment or storage on high levels if you can avoid it. And then avoid those irregularities that I talked about. Plan on areas for lateral bracing if possible. Again, lateral bracing in a steel frame structure is more economical typically than moment frames. And then consider the building height limitations and the allowable seismic force resisting system. So if your building doesn't need to be 160 feet, or you can keep it just under that, then we have more options in the system that we choose. And maybe 160 isn't a great option, but a good example, but maybe more like 65. Oh, another option is you could post a sign that says no earthquakes allowed, but I don't recommend that. So. Well, that's the presentation. I hope it was informative. If anybody has any questions now, I'm happy to answer them, or if you think of something later, feel free to contact me.